So far, this series has approached AI through interaction. We looked at framing, navigation, cognitive load, and the pressure created when the human has to keep steering the system. The question was how interaction with AI can become lighter, less reactive, and less demanding. But interaction never happens alone. It happens inside a system. If the interaction becomes lighter, but the surrounding system becomes heavier, the burden has not disappeared. It has only moved. So before continuing with AI interaction, we need to move one layer down. We need to look at the substrate, not the conversation, not the interface, and not the workflow, but the system that makes the interaction possible. To do that, it helps to step away from AI for a moment and look at one of the most constrained artifacts in a modern product design, the watch. A watch has to live on the body. It has to be small, readable, durable, power efficient, reliable, and useful, while requiring almost no attention from the wearer. In that sense, the watch is not only a timekeeping object, it is a constraint object. And within this constraint-shaped category, the Quartz watch is the dominant volume form. Quartz movement watches account for roughly 3/4 of annual worldwide watch shipments. So if we want to understand which constraints survive at scale, the Quartz watch becomes a natural focal point. This is the bridge back to AI. We are not looking at watches because they are nostalgic. We are looking at them because they show what happens when a highly constrained artifact becomes the mass production answer to a useful function. So, before we return to AI hardware and models, we need to understand the Quartz watch, not as a luxury object, not as a complex object, but as the most widely shipped expression of a constrained product category. That is where the next layer begins. The modern Quartz wristwatch begins with a shift in substrate. In December 1969, Seiko released the Quartz Astron, widely recognized as the first Quartz wristwatch. Its precision was about 5 seconds per month, about 100 times more accurate than conventional mechanical watches of the time. The first model was not yet the cheap, mass-produced object that Quartz watches would later become, but it revealed the direction. Timekeeping could move from a complex mechanical substrate to a stable electronic one. That shift mattered because Quartz changed the conditions around the function. Timekeeping became easier to reproduce, stabilize, miniaturize, and scale. The useful function remained the same, but the system carrying it became lighter. Over time, that lighter substrate became the dominant volume logic of the category. Quartz movement watches account for roughly 3/4 of annual worldwide watch shipments. That is why Quartz matters here. It shows a constrained artifact becoming mass adopted through a hardware profile that reduces burden around the function. The profile is simple. Cost stays low. Running cost stays low. Power demand stays extremely low. The object is quiet in normal operation. The footprint is small. The device is mobile by default. It works as a standalone object. It does not require any extra parts to become useful. It can support several basic functions while remaining bounded. These constraints do not make the object invisible. They make it forgettable. The function remains available while the support system recedes from attention. The user can trust the object without continuously thinking about ownership, power, noise, space, dependency, or setup. That is the hardware lesson we can transpose to AI. If AI interaction is meant to reduce cognitive load, then the machine carrying that interaction must not reintroduce the burden through the substrate. The hardware should support the function without becoming another system the user has to manage. So the next step is to evaluate consumer machines through the same constraint envelope. Not maximum performance in isolation, but minimum additional burden around a useful local AI function. The Quartz watch gave us a pattern. A useful function becomes powerful when the system around it becomes lighter, cheaper, quieter, and easier to carry. Now we apply that same logic to local AI, but in the right order. Before choosing the hardware, we choose the model. As of June 2026, the objective is a capability envelope. Strong reasoning, reliable tool use, long context work, and a footprint small enough for a constrained local machine. The Qwen 3.5 family is the right place to look because its compact models score unusually well for their size. But the model still needs to pass a clear gate before hardware can be evaluated. The gate covers 5 areas: expert logic, deep knowledge, agent coordination, rule compliance, and frontier reasoning. Each benchmark must score above 75, and the average scorecard must be above 80. The model must also be multimodal, stay within the memory target, and support context above 256,000 tokens. The compact candidate is a 9 billion parameter NVIDIA 4-bit floating point model. It passes all benchmarks, including memory, context length, and multimodal criteria, defined by the evaluation gate. To measure capability retention, we compare it against a mixture of experts reference model with 122 billion total parameters and 10 billion active parameters. The compact model retains more than 93% of the reference model's selected scorecard performance. Under that filter, the compact model becomes the primary match. It is not the highest capability model in the comparison. It is the model that keeps enough of the high capability reference, while remaining practical for a compact device. So the model passes on benchmark score, memory footprint, and context length. Now the hardware can be evaluated properly. Lowest financial cost, smallest physical footprint, least noise, and lowest operational burden. The digital Quartz watch gave us the hardware grid. For AI, we keep the same logic. Under $1,000, no metered running cost for the recurring workload, low power under normal use, under 5 decibels, under 1.5 kilograms, ultra mobile, standalone, and versatile. The model has already passed its gate. The remaining question is, which device can carry it with the least operational burden? As of June 2026, consumer options were compared against this grid. The selected device is the MacBook Air 13-inch M4 2025 base configuration, $999, 10-core CPU, 8-core GPU, 16-core neural engine, 16 gigabytes unified memory, 256 gigabytes SSD storage, 120 gigabytes per second memory bandwidth, around 3.5 watts in light use, 15 watts to 22 watts under sustained heavy load, up to 35 watts in short burst workloads, fanless operation under 5 decibels in light use, and 1.24 kilograms weight. This selection can be verified through simple public searches. It supports the selected compact model within the required memory and execution boundary while remaining ultra-mobile, standalone, and versatile. This makes the hardware local first, not local only. The recurring workload can run on-device with predictable cost, while API inference remains available when a task exceeds the local boundary. With the model gate passed and the hardware gate met, the system can now be assembled.